good. Gonna just check like how the online look.
Have you attached the camera? Because
Yes.
it's
It is
not,
at
it's
the,
not on.
it's not on.
No.
Okay. Sometimes it needs first to switch to the computer camera, and when I put it back now, it's already back, and it looks good. Looks really good.
So two things, just first the sound quality.
Sound quality. So you're gonna make the mic check. How is it quality wise? I think it is.
The other one is if you could stand up so that I can adjust the height. I believe it's okay.
There is still a problem, like, okay, so are they exactly in the same network? This is in outer RAM. Where is this connected to? This is in outer RAM too. Everything is perfect except that I'm not able to connect this iPad to the same network. Okay, so it's looking really good. It is finding the same. Okay, the one thing that I can do to make these work is that I can. Okay, let me. I need to ask from the ChatGPT how to make this happen.
What?
Because I need to. Because I was have to install the Keynote in a weekend again. Hmm. Okay, so maybe I need to put this presentation on first. Okay. Can you check like how is a presentation, how this look like? Is it okay?
So just one question: are you sharing the screen, or are you just sharing this?
I'm supposed to share the everything, so that's not
Yes.
correct. That's not correct. So let me see. So it was like video, screen, display. Can you see again?
There's a delay, but it should be fine.
I need to make this a little bigger, like this. Cancel. Okay, and then keynote. There is a 10 seconds delay or something like that. How is it? It looks okay. It looks okay. Hmm.
Okay. So did you start, or are you going?
Yeah,
to
I'm gonna start. Only,
because I have a meeting at 10:30.
yeah, you go. You go.
And when will you finish?
I'm gonna finish at 10 to the noon. 10 to the noon.
Okay.
Hey, thank you. Appreciate that. Appreciate this. So what I did, I'm gonna get started officially momentarily, but I'm gonna explain a few matters to you before I'm gonna go. Just I need to still double check that I am in the same network here. These two need to be connected to my phone. Now this is I guess this is now in the same network. It looked that this is in the same network. This is now connected to my phone. Why this is not willing to connect to my phone? That I don't get it. That's the last thing to do. Can it be connected like this? No. All right. So I want to get started because we are already 7 minutes behind the schedule. So respect. I want to get started by explaining a few practical matters. First of all, I need to apologize that every single week I seems to have some kind of the technical problems with my my YouTube streaming, and that is the case today too. For some reason, my iPad is not willing to connect to my computer, and it's going to be hard to make these drawings. I will try to sort it out this momentarily, but right now it's not working the way I want. Last week it was a problem with the screening system. Every week there seems to be a different kind of problem, which is annoying like hell. And I really spent quite a bit of time yesterday to make sure that everything worked, and it worked nicely yesterday until today it doesn't work well. Anyways, so there is something that I would like you to be aware of, because I mentioned earlier that we only have one written exam in this class, and that is still the case. So we only have one written exam in this class, and the exam will be organized in exam, this exam system, which is a system located in a multiple different cities and universities, and it's going to be available such that the first opportunity to do the exam will be week 9. Week 9 is a Monday, 23rd of February. It's going to be also available in week 10, which is the 2nd of March. I mean, Monday, 2nd of March, and week 11, which is 9th of March that week, and a week 12. That's going to be the last week that is available. And that last week is Monday, 16th of March. So just put it in like clear dates. So it's going to be available from 23rd of February until 22nd of March. So whatever time is good for you, you can already this time to make a reservation to exam place and do the exam whatever time is good for you. And the exam goes in a way that we can only cover the material that we're touching in this period number 3. Period number 4 will be all about AI. So it's not technical, or let me say theoretical matters that we discuss in this 3rd period. So it's something that we feel that should be actually mandatory course for all the students in mechanical engineering. And hopefully it will in later, but right now it's only targeted, I mean, it's all available for those one of you that are specialized in this digital engineering, this class. But in the future, hopefully all the students in mechanical engineering can enjoy it, because we believe that this is a skill that is like almost like mandatory you to have it. Not that you are not aware, know how to use a ChatGPT and others, but it's going to be a little bit deeper understanding comparing just to use a ChatGPT. It's going to give you understanding about surrogates, data-driven models, so on and so forth. Something I personally believe that it is pretty enjoyable stuff. Okay, so that's what will happen once we're covering the material in this class. And this class or this lecture is already lecture number 5. So there is 2 more lectures to go. Next week, there's going to be visiting lecture about the bicycle dynamics. This is something that we do have every single year, and that's going to be delivered by our visiting professor, Aaron Schwab. Bicycle dynamics is an interesting topic because it is a mechanical system that is comes with a surprising behavior. And there's a nice story like how Professor Aaron Schwab started to study the bicycle dynamics, and he wanted to figure out what keeps bicycle in upright position, because bicycle itself is self-stabling system. So if you push the bicycle in a parking slot, it goes automatically in upright position and it stays in upright position. Even when you push bicycle sideways, it's going to vibrate a little bit until the vibration will damp down. So what is the mechanism that keeps the bicycle in upright position, that you're going to learn in next week, Monday, along with the story like what are the other stuff that is important in the bicycles. So those of you that are interested in whatever 2-wheel vehicles you want, it could be bicycles, motorcycles, the same mechanism holds. And I think it is going to be something that you guys are going to enjoy quite a bit. So that's going to be the visiting lecture. And then the one more lecture will be something that I'm going to give a mixture of topics about multi-body system dynamics. Maybe today, if everything goes correctly, everything goes nicely, I will have a time to discuss about the contact modeling. But I would also like to touch about what's the way you can make a use of multi-body system dynamics in fatigue analysis, and how is that you can create the stress histories using multi-body system dynamics. And we can also discuss about mix of other subject matters that's going to be filling up the last theoretical lecture prior to exam. So that's a big plan. That's a big plan. And let me think. Yeah, these AI lectures will be delivered by Sebastian and Greg. So it's not going to be me, but it's going to be these two guys that Sebastian having an office in Lahti. So probably it's going to be at least partially online, but I'm going to tell you the details a little later. So that's what's up. So, right. So, but modal reduction technique, that's a topic that we need to close today. And once we're able to do that, then something a little different. If we have a time, I'm going to explain you something that is called mass invariance. Mass invariance is a way that you're actually combining finite element modeling and multi-body system dynamics. Right. Another final note, practical note, is that if you have complaints about Department of Mechanical Engineering, somehow like loosely related to complaints about Department of Mechanical Engineering, I'm going to be available tomorrow at 10 o'clock. There's something that is called Killed Coffee meeting event. So you're very welcome to join in. And that's going to be in the lecture room that I will tell you momentarily. I don't know if you guys got an invitation. I asked this already a week ago and you said that you haven't heard about it. But if you want like to get to know me like more a casual way, although that is supposed to be a casual meeting too, there's going to be there. How can I see where this is? I don't see the room number, at least in this calendar is not showing that to me. What about this one? No, not that either. Yeah, I'm sorry. I need to take a look at this during the break. So let's have a short break and I will tell you. Can you guys know, are you able to find out what is a lecture room that we're going to have this discussion tomorrow morning? 1247. Okay, so 1247. 1247. So that's located in a building number 1. 2 is going to be, and I think that's the floor where the cafeteria is located, and 20, was it 10, 27? 47. 47. I don't know where that is, but I believe that that's one of the places that are like having this glass wall, right next to the place you can have your lunch. So, meet you guys there.
What's the time?
At 10. Getting started at 10 o'clock. 10 o'clock. And again, is about what are your wishes to the Department of Mechanical Engineering? What do you feel that is off in a Department of Mechanical Engineering? And to try to make you guys, convincing you to participate, I'm going to offer you these stickers. These stickers, these are Beyond Mechanics and other stickers that I offered you earlier, so there's going to be more stickers available. The stuff that like I have here in my computer, like heavy metal meets science, dynamics you can trust, stuff like this kind of stickers. No t-shirts and no coffee cups, unfortunately, but at least stickers. All right, so that's a practical stuff. So hope to see. I'm gonna see you guys tomorrow morning. All right, there's another thing that I need to discuss with you related to Guild, but that's a more like offline topics. I prefer to put the recordings and mics off. Not that it's nothing confidential, but a little bit of your opinions about a few matters. So anyways, let's close what we discussed a week ago. So a week ago we discussed about modal reduction technique. And now this explanation becomes to be difficult because right now I don't have an access to my iPad or my pen. Basically, what we would like to do in a modal reduction technique is that we would like to move from nodal degrees of freedom. And nodal degrees of freedom are these black dots you can see in a cantilever structure. This is what you're analyzing in a finite element software. So you are getting information about how much each of the dots are moving, in this case in a planar space. How much they're moving in X and Y direction, how much they're rotating. So these dots are not particles. They're not particles because they do have a rotational degrees of freedom. They are called nodes. And these nodes, they do carry degrees of freedom. In this case, they carry, well, they can carry 2 degrees of freedom or 3 degrees of freedom. Let's make this in a straightforward way that they're carrying 3 degrees of freedom, meaning that the dot located in a far right configuration can rotate and can translate in 2 different ways. Can rotate in one way, can translate in 2 different ways. As is the case, each of the other dots here. This is how the full model looked like. And we are not happy with the full model. Reason is that this full model consists of overly many degrees of freedom. Even in this simple case, if each of the nodes are carrying 3 degrees of freedom, so we have here 1, 2, 3, 4, 5, 6 nodal locations that multiplied by 3 is going to be 18, which is a little too many for a simple case like cantilever structure you see here. So what we do then is that we are conducting an eigenvalue analysis. An eigenvalue analysis is giving you the understanding about how the structure itself is performing. It's not about actual performance of the response based on the force located in free end of the cantilever beam, but it's more about the structural behavioral properties. Structural behavioral properties, that is a combination of mass and a stiffness. Combination of mass and the stiffness allows you to know what are the natural frequencies of the structure and what are the deformations associated to those frequencies. This structure, as modeled, shown here, will have 18 different eigenvalues. So that means that these have 18 different eigenfrequencies. And each of them are associated to certain kind of deformation modes when the entire are moving in a certain way. Now what we're doing in a modal reduction technique is that we are taking this where the structure can deform. How much they deform in that particular way, that's going to be the new unknowns. So it's called like multiplications of that particular deformation mode. And that allows us to reduce the size of the model significantly with the minimum damage to computational efficiency. Always when you're introducing modal reduction, you're going to lose the accuracy. There's no way to avoid it because more the degrees of freedom, more accurate is your solution. That's the nature of finite element modeling, because finite element modeling is introducing better and better, or let me correct myself, more and more accurate solution, more degrees of freedom you have. But sometimes there may be excessive amount of degrees of freedom, something that it doesn't really make much of a difference anymore. It can influence the 10th digit or something that is not significant, something that we don't care anymore. So you can get rid of those by reducing the size of the model. Even the way you can do this in that you can introduce acceptable damage to your accuracy. Always some damage in accuracy, but if it is acceptable, that's fine. All right, so where this goes? It goes like this. Your original equation of motion is the one that is located here in this upper part of my slide. All right? Unknowns here are these u's. These u's are representing nodal degrees of freedom. In that case, we looked a little while back, so there was 18 degrees of freedom. So this model size is already having 18 unknowns, which is quite a bit. So what we do then is instead of solving the response where the force is located in the right side of the equation, we solving the structural properties, conducting the Eigenvalue analysis. And in Eigenvalue analysis, the first thing to do is that we're going to set the force located in the right side of the equation to be equal to 0. That already tells you that what you're going to get out of this Eigenvalue analysis is not going to be the responses, but the ways structure performs. That's it. All right, so this allows us to get this, something that is called deformation modes. And you can put these deformation modes in a matrix representation, and this matrix representation relates nodal degrees of freedom and modal degrees of freedom. And then when you do that, that can be substituted the original equation of motion, and when you do so, then you can significantly reduce the size of your problem. You can easily go from hundreds of thousands of degrees of freedom to tens of degrees of freedom, sometimes even less than that. And again, the damage you can introduce, the accuracy, will be acceptable. Acceptable, I would say, is the right kind of wording because, like I say, always damage to accuracy. But what's the limit that is acceptable? That's what interests us. All right, now, another great benefit that comes along with the modal reduction technique, the way that it is introduced here, is that these deformation modes will be mathematically orthogonal. So they are not related to each other. And when that's the case, when you multiply the original mass with these modes, you're going to get identity matrix. Identity matrix where the diagonal terms are ones, off diagonal terms are zeros. And the stiffness going to be also diagonal representation such that the eigenvalues going to be located in the diagonal terms of your new stiffness matrix. Big benefit is this, that now you can take any one of these degrees of freedom and solve that knowing nothing about other degrees of freedom because they are independent. They are not related to each other. Okay, so that's modal reduction. That's what we discussed. And the way we can do this eigenvalue analysis, it went like this. Like I said, they're first going to take the force located in the right side of the equation, set that to be equal to 0. And then I do know that the accurate solution for solving this equation is the one that is shown here. One substitute that the original equation, I got two parts of the equation. The one that gives me the eigenvalues. Once I get the eigenvalues, later I can compute the eigenvectors. That's the way it goes. So that's what we discussed a week ago. And one more thing, like I'm pretty sure that this is clear for you, but eigenvalues are representing these natural frequencies, computational form of the natural frequencies, telling me when the system, what are the natural frequency of the structure. Like if I, have the cantilever beam, what would be a good example? This kind of cantilever beam. If I keep on loading this, and if I change my loading frequency, so once the loading frequency hits the natural frequency of the structure, then we're gonna got something that is called resonance. And resonance is very bad condition because then theoretically the amplitude started to increase exponentially, and it's gonna go to infinity. Of course, in reality, it cannot go infinity because there are ways that limits that to happen, but theoretically that's going to be the case. Even in reality, you see this resonance condition all over because those are the cases that you can see there's something vibrating like hell, and the amplitude becomes to be almost like unnaturally high. And that's the resonance condition. The resonance condition, well, I don't know what's the best example, but those of you having the car without any kind of dampers, the car wheel can start bouncing like hell. That's one example of the resonant condition. There's a resonant condition you can find in many different real life applications. But you know what I'm explaining here. Okay, so that's, you're gonna get And then I would like to make a simple exercise here. And again, after the break, I make sure that my iPad is willing to collaborate and I'm able to make a drawings using my iPad. But right now, we need to take a look at this example without my drawings. Okay. What I want to do in this example is that I want to conduct an eigenvalue analysis for the structure that is shown in the upper part of this slide. This is a structure that is like a spring element. This spring element is modeled by using 1, 2, 3 elements. And these 3 elements are connected together in nodal location. Well, this node located in the left side is not connected anywhere at all. This could be connected to boundary environment. But right now there is no connection whatsoever. Second node connects elements number 1 and 2. Third node connects element number 2 and 3. And again, node 4 could be connected to surrounding environment, but is not connected. Meaning that this kind of element is the one that's like floating in a space. There's no connection to surroundings. So it's like this, except there is not even a gravity involved. So something floating in a space. And what we're going to do then is that we're going to take a look at the eigenvalue properties of this particular structure. And the eigenvalues properties, first thing to do is that we need to get the stiffness and the mass. Okay, so I'm going to put this just a little bit aside. So I'm going to constructing system stiff, or they'll say structural stiffness and mass matrices. And if you look at, this is what we practiced a couple of weeks back. This is where the first element stiffness matrix is located at. It's like this 2 by 2 block diagonal representation located in the upper left corner of this structural stiffness matrix. Then there is another element that is located here in the middle. That too is a block diagonal representation of the structural stiffness matrix, the one that is here in the middle, 2 by 2. And now something that is important to recognize here, that this term that is located in our second row, second column, which is a diagonal term, this is where the element properties from the first and second element are summarized. Well, I'm kind of like making these matrices to overlap, and this overlapping component is something that I'm simply summing up this behavior of element number 1 and element number 2. And then I'm combining the element number 2 and 3 in a similar manner. So there's a block diagonal representation. So it's not completely diagonal, but block diagonal. And these blocks are representing the stiffness matrices of each one of these 3 elements. Same way I can construct my mass matrix. And when you look at these matrices, you will soon recognize that it is a matrix that is consisting of 4 rows, 4 columns. These are coming because of the 4 nodal location. Each of the nodal location, 1 degrees of freedom only. What is this 1 degrees of freedom? It is a moving in axial direction. Positive direction or negative direction, but it cannot move a transverse direction, it cannot rotate. So that's why 4 degrees of freedom only. You with me? It's just like something you learn already in a preschool or elementary school. Too simple. It's okay. Level of difficulty is okay. No communication. But no complaints. Okay, all right. Then I do this part first. I'm gonna take my stiffness, and then I'm gonna make the subtract stiffness. From the stiffness, I'm gonna subtract something that is this eigenvalue power 2 multiplied by mass matrix. All right, in computational dynamics, in a computer analysis, this is not the way to conduct an eigenvalue analysis. But I would like just to demonstrate that this is a theoretically possible way to go, and it's not making reality like this because it's not possible to solve the determinant of the system that consists of hundreds of thousands of degrees of freedom. That's going to be practically impossible. Anyways, so now I'm calling my lambda 2, excuse me, my omega 2 by lambda. You see, this is the only notation difference that I did. And then I'm taking determinant here. And when I'm taking determinant from the matrix that eventually will have 4 by 4 dimensions, it's going to read like this. This is a polynomial that is actually fourth order polynomial. How do I know that this is a fourth order polynomial? I know it because look at these lambdas. I multiply with respect to each other. And what I'm after from this equation is that I would like to solve that where the lambda becomes to 0. This is a fourth order polynomial that is crossing the 0 4 times. All right? So when I'm using symbolic math tool to figure out when lambda becomes to be 0, I'm going to get the values 0, 12, 60, and 120. First number is 0. First number 0 means that there is some kind of resonance condition in the frequency, 0 frequency. That's a bit confusing. Like 0 frequency, there's a resonance condition. There cannot be resonance condition in the 0 frequency. But what is it then? What is it that makes the first value to be equal to 0? Seriously, guys? You say rigid body? Did you say rigid body? You all say rigid body. I see that there are many guilty guys here because you say rigid body, you say you say rigid bodies. And that's exactly the way it behaves like that. I'm just a little astonished because usually people don't get it. They don't get like where this 0 is coming from and they're confused like all the time. Exactly like you say. This is a rigid body, so it's not really a resonance frequency. But it's a fact that this system is floating in a space. And because it's floating in a space, we're just looking at the structural behavior. The first values will be zeros, meaning that it can move. Nothing else that it can move as a rigid body. Then comes number 12, 60, and 120. Those are representing the different kind of frequencies that are actually computational natural frequencies. They may be the actual frequencies of the structure depending on how well you have meshed the original structure. They may be accurate or they may be not. This depends on how fine is your finite element mesh. All right, so 12, 60, and 120, those are the deformation modes. Yes, sir?
Can you show me the previous slide, please?
Yes.
Yeah, so like what made the changes in mass matrix when you like made the determinants? Like this mass matrix is different from the one in the.
Is it?
Yeah. Next one. Yeah, next slide.
Let me see. One more. This was a 3,
Yeah.
2.
Yes.
This is different. What else is different?
Yeah, the one in second row, second column.
This one,
Yes.
this one.
Yes.
Yes. They are different. So one is, what is a correct one? It's pretty clear that this is incorrect. Because, what's supposed to be here, this place is supposed to be a mass of the system. And I cannot explain what happened here other than a typing mistake.
Okay.
This is a typing mistake, but what a catch.
No, I just wanted to make sure like something typed.
No, it's a typing mistake, but I'm just astonished that you're really paying attention to these slides. Because I was thinking sometimes when I look at your face, I'm thinking that you're thinking, yeah, all right, so right after lecture today, I'm going to first go to liquor store, and then I'm going to go to grocery store. No, first I'm going to go to grocery store and then liquor store. But you guys are really following. That's fantastic. That's a catch. Thank you. By the way, I might need your observations because I have this major dream of mine. So I would like to publish a book, which is called something. The title of the book is pretty clear. It's called My First Book in the Multibody System Dynamics, and I have my manuscript ready, and I would like to sort it out if there's any typing mistakes. So maybe you could take a look. Maybe you could take a look because you're having the eye to see these typing mistakes. Hopefully I can publish that. My dream is to publish it this year, and that would be it would be nice to put it in a Christmas market because that would be I think I'd like selling like no limit. You know, everyone would like to get this kind of like a hard Christmas present. Okay, back where we were. So we were here. So we got these numbers that are telling the deformation frequencies. And like I said, they may be accurate, they may be corresponding to reality, maybe not. As a rule of thumb, when you have a thin mesh, it is okay to assume that the lowest frequencies are pretty much accurately modeled, and those are the ones you can see in reality too. But the higher you go with your frequencies, the more you introduce mistakes, errors. And typically the higher frequencies are not something you can find in reality. At least the difference becomes to be easily pretty significant. Okay, so we're here. Now what follows is that we're gonna take each one of these values, put it back here, and then solving this guy here. This is a vector of unknown consisting of 4 components. And these 4 components are associated to 4 degrees of freedom. And it's gonna give me the way the structure deforms in that particular eigenvalue value. So I'm gonna take my number 12, gonna put it at this part of the equation. This is what I'm gonna get. When I multiply the matrix with the corresponding vector, I will get the 4 equations for unknowns. All right, so we know that there is a way to solve that too. And once I solve it, it's gonna look like this. I'm gonna get the values, which is a -2, -1, 1, 2. This is something that I can multiply this vector by any number I want. And it's still gonna fulfill the equation that I looked in my previous slide. This one here. So I can put any number here and still it's gonna be equal to 0. That means that these deformation modes are nothing but the modes. You cannot look like absolute values because they have no clear meaning. So if you look at like -1, this is not like -2 meters. It's not -2 meters, but it's how much this node is moving relatively with respect to its neighboring nodes. Nothing else than that. And this is a typical mistake that people are considering these deformation modes to be something that is an absolute deformation values. And they're sometimes measuring the values considering that this is an amplitude. No, it's not an amplitude. That's not just what it is. It is just representing the way structure can deform. This way is simply like if you have originally equally divided elements, the first node is going to move in a negative direction amount that is -2. It could be also multiplied by 0.5, then this will be -1. Second is going to move -1. Again, if you multiply that by 0.5, it's going to be 0.5. And then this one is going to move in an opposite direction, So it's nothing but the deformation mode, which is like, this kind of like a spring mode that the system is linearly compressing and getting longer. Like this is a mode, how it looked like. Second mode is a little bit more complicated, and it's going to be hard to visualize when I'm not able to use my iPad. But the first mode is moving negative direction, second one is moving positive direction, third one is moving again negative direction, and then the positive direction. It's almost like there's a wave that is traveling through the structure. That's how it looked like. And then there's one more complicated than that, And again, it's more complicated way that the structure deformation is represented. Makes sense. Makes sense. All right, good thing. I said earlier that you can multiply these deformation vectors by any number you want. And sometimes they are multiplied by number, and there's a particular target when doing so, because typically these deformation vectors are scaled. You know, in a computer analysis, it's always a good idea to try to put all the numbers as close to 1 as possible, because computer hates very small numbers. If you have like 1 power minus, multiplied by 10 power minus 12, this is going to be very complicated for computers because they are not comfortable with very small numbers. It's equally difficult if you have very high numbers. So if you have the same number but 10 power to 12, that's again very high number that is going to be hard for computers to deal with. So basically the computers, what they really love is all the numbers that are as close to them 1 as possible. So one of the ways to make a computer's life a bit more pleasant is that you can scale each of these deformation modes by using your mass matrix. And then this is called mass scaling. This is mass normalization that is called. It basically means that you're going to select their numbers, more accurately select the deformation modes, such that when you multiply your original mass matrix with the deformation modes, you will get this identity matrix we looked in a little while back. All right, what is this number then? That is called scaling number. That depends on the case. When I take my first deformation mode, which was again -2, -1, 1, 2, I multiply that with this unknown multiplication factor or scaling factor, and setting this equation to be equal to 1. This is the way that I can solve this alpha 2. And alpha 2 in this particular case is the square root 1 divided by 5 in this particular case. But each of the modes need to be scaled separately. When you scale a second mode, is again alpha 4. This is a deformation mode. This, by the way, I think it is supposed to be, no, this is correct. This is alpha 4. You're going to get the scaling number that turned out to be 1. So there's no scaling at all. When you're using the scaled deformation ways, multiply your original mass matrix, you will get the identity matrix. This is what we were aiming for. And then in the stiffness, you're going to get your eigenvalues as your diagonal components. That's how it works. All right, now, here's what I'm proposing. I would like to propose a break here because I would like to force this iPad to cooperate. So let's have a short break, like 5 minutes. And while you guys are stretching a little bit, I'm going to connect my iPad to my computer so then I can start doing my drawings. All right? So that's the way to go. 5 minutes. Like this. So what I wanted to discuss was that, are you guys aware of this kilt of mechanical engineering?
Yeah, I've been there a couple of times.
You've been there?
Yeah.
Ah, you've been there.
Mm.
Okay, is it who is the one that is it yes the officer that is saying that it makes sense you to participate, or somebody else?
We are we are doing a project course, so we go there and discuss as a group. Yeah.
Oh, nice, nice. So are you planning to come tomorrow too?
Yeah.
Nice, nice. That's really nice. Because sometimes I'm a little worried, like the kilt is, somehow the international students are not heavily involved with the kilt. My reasoning is this. You know, we don't have any like international students or domestic students. We only have LUT students. That's it. That's it. And everyone should be participating to Guild. Everyone should do this and that as a team, one team only. That's my big dream, to see that to happen. And I think we're getting closer to that. And I would like to discuss tomorrow what is the way that the department can encourage to have just the one guild that is serving all the students, not just students focusing in a master level or a student focusing in a bachelor level studies, but all the students in the Department of Mechanical Engineering. If there is a way to do that, would be really nice to hear that. I don't know if there's a way to do it. Okay, so now I'm gonna work with this guy. Could this be the fact that because they're complaining that my software is not updated and is, don't know. There, now it looks looking better. Cannot join this. Uh-huh. They are in the same network, so why come they don't want it to connect? I just don't get it. To get this thing, like file. Yeah, they are in the same network. No, they're not, because they're, okay, so maybe this is gonna be solved. Yep, now just connect. It may be because this software is not updated. Could be that. I don't find any other reason than that. But it's going to take a while. Hmm. Mm-hmm. Okay, so I'm able to use my phone in that purposes. I but still not willing to do it. Okay, loading. Mm-hmm. Keynote. Okay, so I'm able to do it like this. Uh-huh. All right, so at least something. So this is better than nothing. Still not perfect. So it was, I know what was a big problem. So big problem was that I was forced to install my Keynote, which is the software that I'm using to show my slides. yesterday, and there was a settings that was not correctly made. So now at least I can make a drawing some kind. It's not going to be very good, but it's going to be my phone based. So it's better than nothing, better than nothing. So at least I can show a few things to you, because the explanation becomes to be very complicated if not able to make any kind of drawings. So just want to connect. This is going to be the last thing to do, connecting this one. So it wasn't the problem about the network or anything like that. It was all the time the settings in Keynote software. Okay, so Bluetooth. All right, so the pen is not willing to connect to that, but I can use my finger, which is better than nothing. Okay, but this guy is now back in operation too. Okay. Let me see. Keynote. Unlink this. Elderom. Okay, not then. My finger. I just cannot make it happen today. It's not possible. It's a big shame. It is just a big shame. Very low performance from my side. I'm super sorry about that. I thought that everything was correctly made, but it was not the case. Really sorry about this. Anyways, we need to continue the story here. You guys don't see this, so this is connected. Yep. Dock 2. Good. All right. Here's kind of like a conclusion of what happens when you have a reduced model. You know, what we did, we started from the model that consists of 4 degrees of freedom. And then we select 2 modes corresponding natural frequencies to reduce the size of the model. We reduce the size of the model by multiplying the original stiffness matrix by these 2 assumed deformation modes. What we're gonna get as a result of that was that we're gonna get the matrix that is a 2x2 identity matrix, representing our model mass. And then we got another matrix that was a diagonal matrix, 2 by 2 diagonal matrix, where the natural frequency or eigenvalues are located in a diagonal term. Look what we did. So we select the mode number 2 and mode number 4. So you don't need to select those in a row, but you can select the one you feel that are the most significant ones. You can easily reject whatever you feel that is not really beneficial for you. And we thought maybe this was incorrect assume, but we assumed that the mode number 3 is not significant for us, so we took that away. We also took the mode number 1 away because that was representing the rigid body motion for us. And rigid body motion, we really don't care because we really are concerned about deformation cases. All right, then we got the vector that is introduced into force, and force here is located in a node located in the right end of the structure, and that is converted to be in a modal coordinates with help of the, again, assumed deformation matrix. When you do that, you're going to get this as your final equation of motion. Final equation of motion is super pleasant because you can take mode number 1, solve it, knowing nothing about mode number 2. Mode number 2 is now the one that was associated to frequency 120 hertz, not hertz, but 120 as a number, and the first one is at 12. And again, you can just solve the one, solve the second, and the way you can get back to something that makes more sense to you is that you can always reverse back by making a relation between the modal coordinates and nodal degrees of freedom. Modal coordinates and the nodal degrees of freedom goes like this. This is what you're going to solve from your equations of motion, and then you're going to go back to your nodal degrees of freedom using your assumed deformation modes. And typically, this is what you're interested in. So these nodal degrees of freedom is something that already carries certain value, design value. Not necessarily the one that you're most interested in, because most of the design is made, this kind of made is to get strains and stresses. Not so much about strains, because strains are not too relevant for us, but stresses are very relevant. So what you can then do is that you can use the technique we discussed a little while back. Yes? Is in the YouTube they don't change. Okay, so I need to put this back on. Display capture was the one that I used earlier. Can you see how things look in the YouTube? There is a few seconds delay. Is it any better? Is it still the same, or now it looks good? Yeah, I really want to make myself to look smart, and that's why this YouTube and everything, all these a lot of gags here and there, but technology is just against me. What are you gonna do? What are you gonna do? I thought that I'm more clever than I am, which is my typical mistake. So I really feel bad about that. This class so far, almost every single week, some kind of the problem. But I'm gonna give you the promise. But 2 remaining lectures we have in this period gonna go smoothly, because the next one is gonna be this visiting lecture delivered by Arenswap. He's using YouTube, every day, almost every day. So I think it's going to go well. And then the last one that will be delivered by me, I'm going to really practice myself on Sunday until every single detail is correct. All right. So, yeah, what I was about to explain, that this displacement, which is a deformation, how much things are deforming, we usually don't care so much about deformation, but we do care a lot about the stresses. What you could do with this U is that you can use something we discussed, we call as a kinematic matrix that relates nodal displacement and strains, which is already almost what we're looking for. So you can use this kinematic matrix to get the strains. And from strains you can use elastic coefficient, sometimes called elastic coefficient matrix, depending on the degrees of freedom you're dealing with, and then you can get the stresses. And that's what you really are after. So that's the way you can close the case, the entire case. All right, now comes something that is that definitely requires me to be able to make a drawings. I'm asking you the following question. What we did in this first example was that we said that the structure float in a space, so there were no boundaries involved. So it was just like floating in a space, and the deformation mode looked correspondingly like this. They were like something like this. And I'm wondering if this is the correct way to go, because there are alternatives available. And I would like to take a look at these alternatives by looking at the crankshaft mechanism. And in the crankshaft mechanism, let's take a close look about the connection rod that is connected to piston and the crankshaft. The connection to piston is via revolute joint. Connection to crank is via revolute joint. So basically, the kind of like limitations that I have is that both ends of the connection rod have to be close to the nodal location. And I wonder what's the right way to set my boundary condition. Boundary condition that I can use to compute my eigenvalues. The option first is that I can set the boundary condition the way that I did in my example a little while back, meaning no boundaries. There is nothing that connects my finite element model to any of the surrounding elements. So there is nothing. And I could get the deformation mode look like a banana here, so it's something that is pretty much like a banana mode. And then another option would be that I can use a simply supported beam condition, where I have this one here, the left end connected to ground via beam joint, and the right end connected to ground via simply supported condition. So only the motion in a y direction is constrained. Or option 4, which is that I'm going to use a cantilever beam connection. And in my cantilever beam connection, the left end is connected to boundary, rest is remained to be free. Now my question to you is that which one of these is the correct way to set your boundary condition? And I'm going to ask this in my first in-class quiz. So which is the correct method to use? Is it going to be A, B, C, or D? And the D is referring some other way, not shown in the slide. So what do you guys think is the right way to go? And go ahead, and I think the circuit is supposed to be open. I'm going to double check that. There. Okay. So the method A, B, and C, and to see what are the methods, they're shown not here, but here. Okay. What do you guys think? What's your thoughts about this? What is your initial thought? What is the correct way to go? No thoughts. Okay, so let me I'm gonna take a look at the Socrates one more time, and then we're gonna move on. So we got 13 answers only, 14 and counting. So it's getting higher. 14. If I look at my YouTube followers, where's my YouTube? I don't know how many people are following in YouTube. That's a little hard to tell based on this. Okay, anyways, so the number is counting. I want to show you the correct answer. The correct answer is it doesn't really matter. It doesn't really matter. So every one of you will get the points out of this. This is a surprising thing because it doesn't really matter. This needs some explanation because seriously, is it really the case that it doesn't really matter? And let me see, this is not my keynote. Keynote is here. So it doesn't really matter. So is it really the case like that? In this particular case, it is like that. I cannot make a general statement that it never matters. Sometimes it can matter, but in a case like this, it doesn't really matter. And that's, one of you may argue, but hey, come on, wait a minute, because each of these deformation modes are associated to different natural frequencies. So if you look at the natural frequencies associated, the lowest deformation modes, in the case that is method A, like system is floating in a space. The natural frequency could be, of course, depending on the parameters, material parameters and length and such. We can call it that this is probably going to be something like 50 hertz. And when you look at the second one, which is the simply supported beam condition, it's going to be stiffer boundary condition. And corresponding natural frequency will go higher, which could be like 65 hertz. And then the one that is C is going to be even higher than that. So that's going to be like 75 hertz. Like, am I really claiming that same body can have multiple different natural frequencies? And my answer is no, I'm not saying that. But I'm saying that your natural frequency depends on the reference condition. What is this reference condition? Reference condition means that how you bind, how you combine your structure to your environment. And now we saw that we have three options. The one that is not connected at all, floating in a space, simply supported, and the cantilever beam. Those doesn't really matter because each of them will give the same, approximately same responses. And why is this? Because reference condition here is just something that gives us the way to see the final configuration. And this is now impossible to explain without drawing this to you. So let me try to draw this to you in a way that I'm going to make my, let me see if I can make my mouse to be my drawing tool here. Let's make it a little bigger first. Okay, so I figured I will make the drawing using this this software, which is PowerPoint software here. Okay, so can you please check that online participant can see roughly the same that you guys can see? Okay, is they don't see the same? No, this is a blank. I'm gonna start making drawings. This. Yeah, they see the same. All right. So again, this was what we were looking for. It was like connection rod, like this one. Okay. Let's make this in a system that it is. This is a crank. This is a connection rod, and it's deforming heavily, like this, and then it's connected to your piston here. So deformation probably never going to be this big. If it is this big, I think you have a pretty serious problem in your engine. But let's make a drawing like this. What we really are wondering, what we really wanted to do is that we would like to see how is a response, how is a particle rotation with respect to this global coordinate system, the reference coordinate system. I'm going to make this a little bigger momentarily. And then you would like to see how is this point here, I'm going to change the color here, this point here, located with respect to this guy. And I'm going to make this a little bigger. This drawing, this wasn't a really good idea. I need this one bigger. So this was a reference coordinate system, located here. And then I'm going to just focus in on my connection rod, like this one. Now I would like to go here, which is where the particle is located. It's in the middle of the structure. And I can travel this in 3 different ways. I can first of all go in a way that I'm going to use as a free boundary condition, which means that the system is floating in a space. This is what happens in this case, roughly, because remember what I showed you in my previous slide. This deformation mode was like this. This is what I saw you, right? Okay, this is not exactly in the right location, but roughly you got the concept. What happens when you have the boundary condition like this, in a free boundary condition, this body reference coordinate system is not attached to any of the material points, so it's not located at this point that it was in undeformed configuration attached, but it's detached to this point. Also, it's not following the orientation of this point, because if it would be the case like this. But that's not the case. So it's detaching itself from the material point. And this is, by the way, why the name floating frame of reference formulation is coming from. Because the coordinate system is traveling with the body, it is rotating with the body, but at the same time it's floating with the body. And this floating comes when the body deforms, and then the reference coordinate system is detached from the material point amount of the deformation. So that's where the name floating frame of reference formulation, it is coming from. So it's floating with the body. All right, but again, I want to travel to this point, and I will travel this point by first going here, and then from here I'm going to go here. This is where my final destination look like this. Now I can do the same by using the second boundary condition that was like this. Second boundary condition was that, okay, now the reference coordinate system is actually attached to the material point, like shown here, but it wasn't following the rotation. So I can put my body reference coordinate system like this. Now what I do in a dynamics is that now I need to change the color to make this more clear to you. So I'm going to travel from here to here, and then here. And what's the big difference? No difference. My final destination is still same. It's all the time same. Okay, my final option is that, okay, I'm using this, let's use this as this color. So my final position was that I'm going to make it like deformation like this, and it was the body reference coordinate system that was following the material point and orientation. This is how it looked. This was this, sorry, the low quality drawing, but you got my point. This is a cantilever structure. That would mean that this body reference coordinate system would be pointing this way. And again, if I traveling here first, this body reference coordinate system and then this material point, again, the same final destination. So no difference. So big lesson to learn is that your natural frequencies depends on your reference condition. What is your reference coordinate system? That's what matters. And we don't really care about the frequencies, but we care about the way structure can deform. And if I take myself back to this guy here, if you take a close look about the way structure deformed, each of the banana mode is roughly the same. They are roughly the same banana mode. So that's a kind of the lesson to learn. Natural frequency and corresponding deformation modes are linear dynamics. We don't do linear dynamics here because whatever you are getting the eigenvalues and eigenvectors, you're linearizing your system. You have to use a linear system. We don't care about the linear piece of the solution. We care about the final solution, which is nonlinear solution. So that's why each of them will get roughly approximately same responses, which is quite surprising, Okay, now comes another in-class quiz. Yeah, this doesn't matter, and here was the idea to make me to make my good drawings, but I wasn't able to do that. What the floating means in the floating reference formulation. It means that the formulation is still under development because it's a floating towards the to fully developed form. It means that the body inertia can fluctuate, the body mass can change. It means that the strains within the flexible bodies can be defined easily. It means that the body reference coordinate system can move from a material point of the body. So what is the correct answer? Okay, and then let me put this one here back. Fine. Guys, I really appreciate that there was 39 answers. And I really appreciate that, because if I would be you, if I would be in your position following this pretty unstable technical presentation, I would be probably leaving. I'm not following my lectures ever anymore. And I really appreciate, and I really apologizing. And this is the last time that I'm apologizing. I'm forgetting, because I don't want to apologize that I'm apologizing. Okay, right, but this is my next in-class quiz, and the question was, still is, what the floating means, where the name floating is coming for the floating film reference formulation. What are and the options you can see here? Okay, I'm gonna revisit that momentarily, and then I'm gonna just move forward and close the case. Now there's a method that maybe Jussi already have mentioned this to you. This is the very often used method to get these deformation modes, and it's called Craig-Pampton method, and this is something that most of the commercial software are using that. Reason being that if you only use this vibration modes, certain details gonna be hard to describe accurately, because these deformation modes that are based on the eigenvalue analysis tend to be symmetric. And if there is an asymmetric loading condition, asymmetric boundary condition, they become to be hard to describe by using these eigenvalues only. So that's why there was a method developed that is a combination of eigenvalues as something that is asymmetric detail description. And that method is called Craig-Pampton method. Craig-Pampton method is based on the fact that you're dividing your number of degrees of freedom, or let's say nodal locations, to two different categories. Something that you're highly interested in, something that you're expecting to see asymmetric loading, boundary condition, joint connections, something that your point of interest, let's put it this way, and those points will be called as a boundary degrees of freedom, and the rest will be interior degrees of freedom. So that's basically the choice you need to do. And this is the choice that the user is expecting to do. So basically, once you have the model ready in your final element software, this case is a plate kind of the structure modeled by using plate elements. Then it's just clicking that I'm actually interested in this corner that is located here in left end, another corner also located in the left end. Those are probably the locations that there's either heavy loading or there's a joint related to these points. Okay, this is what you need to do as a user of those software. Everything from that on will be automatically made. What's automatically made then is something that the mass and the stiffness within the software will be reorganized. And it's going to be reorganized such that boundary degrees of freedom will be reorganized as a upper part of the upper left corner of your mass matrix, upper left corner of your stiffness matrix, and the interior degrees of freedom will be located in a lower left corner. Keep in mind that the interior degrees of freedom is number-wise significantly larger than the boundary degrees of freedom. All right, then there's of course this mixed when the things are combined, because now we can just take 1 degree of freedom and look the 1 degree of freedom only, because in a final term modeling things are related. What follows is I'm not going to make a use of the part of these equations gonna first take a look at this interior degrees of freedom, the one that was located lower right end, here and here. Gonna take these submatrices, and I'm gonna conduct an eigenvalue analysis based on those submatrices. That means that, basically it means the following. It means that I'm gonna take these boundary condition and attach them to the boundary as a fixed joint. So there will be fixed joint located in both corner of this plate element. And then I'm solving something that is eigenvalue analysis such that there is a fully fixed boundary condition associated with each of these boundary degrees of freedom. All right, what I'm gonna get is a deformation mode that are vibrating, but still these boundary degrees of freedom are keeping that connected to ground. So it cannot move freely to space, it cannot just float like was the case earlier, but it is connected to your surroundings. Then what happens is I'm not going to compute another set of modes, and this other set of modes is something that I'm going to introduce a unit displacement to these boundary degrees of freedom, one at a time. So if I have this kind of beam element, and I'm selecting this to be my boundary degrees of freedom, and this to be my boundary degrees of freedom, I'm going to introduce the unit displacement to all the degrees of freedom in this particular location here, such that this is going to move unit displacement this direction, unit displacement this direction, rotate unit amount. Same for this one, and this one, and this one. And I'm going to get another set of modes, which is called, I don't even remember, this was a static correction modes, something that they have a very severe local deformation, something that is a very heavy local deformation, which gives me another set of modes. Then that's it. That's my modes. So they look like this. So if I would have this kind of like a beam structure, and now I'm assuming that in a beam structure, I'm selecting this end, and node in the middle to be my boundary degrees of freedom. Now boundary degrees of freedom means that these points will be attached fully to the ground, and then I'm just computing the eigenvalue for rest of the structure. And it means that basically you will get something that here translation and rotation is not allowed, same here, and the rest can vibrate as it wants. And we can get many vibration modes using this kind of the reference condition. And then this other set of modes was the static correction modes, where this unit displacement is introduced each one of these three locations, one at a time. Fine. So that's it. I got combination of two different kind of modes, and this is where I could stop. I could be happy with that, and typically softwares are not stopped there. And the reason is this. You know, the static correction modes, these ones are not orthogonal, because they are based on displacement. So you cannot get it orthogonal. If you can get them orthogonal, that's going to be pure luck. But generally speaking, they are not. Which is something you can live with, but some people are like, okay, definitely this is not a good idea, because mode's supposed to be orthogonal to make sure that eventually you will get this diagonal representation. And now this other set of modes is not. So what's typically being made is that you're forcing them to be orthogonal using technique that is called orthonormalization. That's a name monster, but basically you're putting these two set of modes together. You're comparing the new stiffness and mass, which is not going to be diagonal because of this guy is not orthogonal. The static correction mode is not orthogonal. And then you're going to conduct another eigenvalue analysis. And then you're going to force each of the deformation to be orthogonal. Again, not necessarily needed. You can stop there, but most of the commercial software, they don't want to stop there. They want to go all the way until every single mode is orthogonal. All right, so this is where you're going to get the new set of mass, stiffness. You're going to take this new set of mass and stiffness, conduct another eigenvalue analysis, and then you're gonna get the modes that are fully orthogonal. And when you do that, now your final stiffness, final mass will be diagonal representation. Is it really necessary to go all the way? No, it's absolutely not needed, but many people are doing that. Okay, this is ANSYS software, so this is how the modes look like, and then you're using this orthonormalization, because orthonormalization, each of the modes will be looking different. One of the modes, so you're already here.
Yeah, a few minutes earlier.
What did I say? 10 to the, no.
Yes, you said
All right.
a few minutes.
All right, okay, so we're gonna get something that is approximately free modes, and something that is approximately boundary modes. That's it. That's basically where I can end. But again, it's okay to end here too. So you don't necessarily need this orthonormalization because it's just a beauty mistake, but not major beauty mistake. All right, let me see what I have here. All right, this is selection of modes. This is something we can discuss, not next week, because next week is going to be Arend. Arend, by the way, is not the regular professor, but he's a fantastic guy because, you know, this TED Talk. Have you ever followed the TED Talk? So he's been in a TED Talk. Guess what was the subject matter? Bicycle dynamics, of course. But not just that. But you know, what is that we all, as an engineer, what is that we're dreaming for? We're dreaming for to get ourselves in a Bible of the engineering, which is called Technical Maailma. That's where if you find your way to that magazine, that's going to be like lifetime accomplishment. And he did that too. They interviewed him in that magazine. Unfortunately, that magazine is in Finnish only. Yeah, but you guys are following that, of course. Of course. So he was there because he published a story about this bicycle dynamics in Science. You know, there's top journals that are Nature and Science. So he made a story about what keeps a bicycle in upright position, and he published that in Science. Okay, so what keeps bicycle in upright position? Come here next week, Monday, and learn that. He's gonna explain all the details. Okay, that's it. So next week it's gonna be Arend. The week after that, we'll make sure that no technical mistakes whatsoever. I'm gonna see you guys in a week from now, and this is when I'm gonna close my recording.